Now that we have a two-dimensional picture and a three-dimensional picture of molecules, or at least a way of like representing them on paper and thinking about it, we're going to use that three-dimensional picture to build further and start thinking about molecular polarity. So this will allow us to understand the physical properties of the molecule better, and it'll allow us to understand how it forms solutions with other compounds. And that's going to give us a lot of information about how we can extract it out of plants, how we can manipulate any sort of molecule. But it's going to depend a lot on its polarity. And so let's walk through what that means. So the shape of a molecule in 3 dimensions is really going to help us understand how the electrons are distributed in 3 dimensions. And it turns out it's not like perfectly even. Like we don't have the electrons spread around in a completely uniform way throughout a molecule. And when we're thinking about the outer sphere electrons that are participating in lone pairs or in bonds, there's an unevenness to it. And polarity is a measure of that unevenness in how the electrons are spread around. And that can happen within the whole molecule, but we can also even think about it within just one of the bonds. And what it comes down to, the reason we see this unevenness instead of it just equally spread around is because some atoms nucleuses are better at pulling in electrons and attracting it to it. And that's because they have different numbers of protons, right? And different sizes overall. And so that impacts the ability for it to attract electrons. And we gave it a whole property name. It's called electronegativity. Right here. I've got it down here. I'll talk about it. And so we make predictions about the polarity of the overall molecule or about a bond based on that electronegativity property of the different elements. And we can compare them and kind of get an idea of which one's going to be stronger than the other. And what we get is we get this kind of picture. Here's water again. So this is water. It's oxygen bonded to 2 hydrogen. In this case, the oxygen is more electronegative. And the hydrogens are less electronegative. Which means that the oxygen is going to be better at attracting electrons. Which means the electrons are going to spend more time around the oxygen than those hydrogens. And what this kind of picture that I have here is showing is that the red versus blue is that we have more electron. We call it electron density, that it's more likely to find the electron around the oxygen. It just means that it spends more time over there. Versus this blue area by the hydrogens. And so we actually end up with the molecule kind of has a half that has more electrons and a half that has less electrons. And that's actually creates, well, it's not a full positive or negative charge like we saw with ions. It's kind of similar. We call it a partial charge. And so we're going to represent that partial charge with a little delta symbol. I'll show you. It's the lowercase delta. So we'll have a partial negative charge where there's lots more, or where the electrons spend more time. And we're going to represent with a lowercase delta. It looks like that. And a negative symbol to be like there's not a whole -1 charge, but part of one. And we're going to have a partial positive charge by the hydrogen. So we can represent that with a delta plus. Another way that we can represent this is with what we call a dipole arrow. We'll represent it by putting a little plus symbol on one end of an arrow and have it point. And so this is going to be a dipole arrow where the positive end of the arrow is at the partial positive end of the molecule. And the arrow points at the partial negative end. And so here that the negative end is always going to be pointing towards the lone pairs of the oxygen, essentially. So we're going to measure this electronegativity. Well, we're not going to measure it in the lab, but someone else did. So through a series of experiments, we have this idea of relative electronegativity between the elements. And there's variation within this. There's a number of these versions of tables based on the way it was measured. And so there's variation. But this is one we're going to use, and if you use others, it's fine. And that there is a pattern. We know that fluorine is the most electronegative right here. Notice that the noble gases we don't have measurements for, it's not relative, because they're not going to be participating in bonds. And so this is really looking at shared electrons being attracted to a nucleus. And so since our noble gases typically don't participate in covalent bonding, we're just not including them. So our fluorine is the most electronegative. You can see rubidium down here is really low, right? And our electronegativity increases as you go across the periodic table and up the periodic table. And so the way I think about it is the closer you are to fluorine, the higher your electronegativity tends to be. And that means that fluorine is really good at attracting shared electrons. So these values are electronegativity values. And we're going to look at the differences between these numbers to understand if a bond is polar or nonpolar. So let's take an example of let's do oxygen and hydrogen, right? Because we were looking at water earlier. So this bond right here between the oxygen and the hydrogen, I'm going to compare the electronegativity values of them. Let's find it. Here's oxygen and here's hydrogen right here. So my oxygen has an electronegativity value of 3.5 and my hydrogen has one of 2.1. So I'm just going to take the difference between the two, which means subtract. So, and I represent this as delta, the difference between my electronegativities would be 3.5 minus 2.1, which will give me 1.4. So that's going to be the difference for just this one bond. It's going to be the same here too, right? Because it's the same bond. And I'm going to use that information to decide if it's a polar bond or a nonpolar bond. And polar just means that it's going to have uneven distribution of electrons. And so we'd get that kind of dipole arrow situation. And nonpolar means that, the electrons might not be perfectly shared, but they're even enough that we don't see a really noticeable difference in how they're distributed around the molecule. So we're going to have categories here. If the electronegativity difference between two atoms is a value that falls between 0 and 0.4, we're going to call that a non-polar bond. And we're going to say that this means that, this means that the electrons are shared evenly-ish. If it falls between 0.5 and 1.9, then we're going to call this a polar bond. And this means that the electrons are not shared evenly. And so you would have a partial positive and a partial negative charge exist. And you can represent that with a dipole arrow. And if anything is larger than 1.9, then it is really, really different, right? If it's larger than 1.9, we actually see these become ionic bonds. And you can see the electronegativity values of the metals are really, really low. And so if they're paired with something that is a nonmetal, that difference is so large, it's larger than 1.9. So in that case, the electrons aren't shared at all. So if we come back up and we look at this value for our oxygen example, right? This 1.4 value is in that 0.5 to 1.9 range. Therefore, it's polar. So each of these bonds right here, these are both polar bonds. And knowing that information then allows us to determine if the molecule overall would be polar. And that's going to require looking at this in 3 dimensions. So let's walk through it for water and show that step by step and then look at the geometry. So if you were given something like you're asked to determine the molecular polarity of a molecule, you're going to first take your Lewis dot structure, we did for our oxygen, and you're going to interpret that into a 3D structure. Because the geometry around the central atom is going to be really key to knowing if those partial positive and negative charges create a symmetrical distribution of charge or an asymmetrical distribution of charge. So our water molecule's Lewis structure looks like this. So when we interpret that into 3D, we learn that it's bent because we have these lone pairs pushing down. So here's our 3D picture. It's bent. We know this is about 105 to 109. And now with this picture in our minds, we can establish if we have an overall polar molecule. We will, once we have our 3D picture, we will go through and calculate the difference in electronegativities for each of our bonds. And so we did that just earlier, so we can put that in. We would probably track our electronegativities, and that would help us understand that each of these bonds has a electronegativity difference of 1.4, which puts us in the polar bond region. And so each of these bonds are polar. And I can represent that a few ways. I can either say that this is delta positive and this is delta negative, like to show that there's partial negative charge on the oxygen and partial positive charge on the hydrogens. I could use small dipole arrows too along the bond and write them right along it to kind of show, oh, the positive end's over by the hydrogen and it points to the more negative of the 2 atoms bonded, which would be the oxygen. Or I can draw, well, yeah, those are the 2 things. I'll get to the next one next. So once I identify where my polar bonds are and I have my 3D geometry, I can now decide if they're the polar bonds in the molecule, if the overall molecule is polar. And so just redrawing that water molecule. I had these 2 polar bonds. I'm going to try to decide if this is polar or non-polar overall. And if I have a polar bond, it's most likely going to be a polar molecule. This has an asymmetry to the geometry because of the lone pairs on the oxygen, creating that bent structure. And so I can see that I have a buildup of positive ends here on one end of my molecule, and they're both pointing in the same direction. And so I would call this overall polar. I could represent it with a dipole arrow that covers the entire molecule like I did there in pink. We find that the times that you have a polar bond but no overall polarity, and so like no unevenness, is when the uneven electron distribution in the bonds is actually symmetrical over the entire molecule. And so an example of that would probably be something that has no lone pairs in that central atom. So like oxygen already always has lone pairs. So like that's not going to be the case typically, or sulfur or nitrogen. So let's look at something like carbon, which usually has 4 bonds to it. So it has a lot of symmetry, right? There's no lone pairs on a carbon. So if we had, let's say, something that was more electronegative than carbon, like fluorine, all the way around it, me give it us lone pairs. Let's walk through the process for this. So the electronegativity value for fluorine is 4.0, and for carbon, it's 2.5. And so since all of these bonds are the same, we're all going to have the same electronegativity difference, which is that 4.0 minus 2.5, which is going to be a value of 1.5. So that falls into our range of 0.5 to 1.9. So we have polar bonds. So all of these bonds are polar. I'm going to represent them with, you could either do the delta negative on these, because the fluorine is more electronegative, so it's going to do a better job of grabbing all those electrons. And then carbon's going to have a lower electronegativity, so it'll kind of have the electrons around it less. So I could put a delta positive. I could also put little dipole arrows as well. I like the dipole arrows because they kind of help me think about like directionality. I don't know. And then the question is this symmetrical? Like I have polar bonds, but it's totally symmetrical without lone pairs. And so all of these are going to be essentially pulling electrons in the opposite directions from one another, perfectly spaced apart, that it's going to create an unevenness in each bond that is symmetrical on the whole. And this is overall going to be nonpolar. There won't be an unevenness to it because its unevenness is even. It's confusing. So in our next video, we'll walk through a few examples.